Hello, today I'm going to present a way of drawing circuits in Factorio. The idea is that sometimes you might have a circuit that doesn't work exactly as you want, and you want to analyze what's going wrong with it. But if you have, say, a bunch of combinators, it's going to take forever for you to figure out what's going on in each of them. So here I give you a way of representing the circuit systematically into a table, and then you can follow an algorithm to calculate what happens in the circuit, like an emotionless machine. I think that's what we are, players of Factorio. Now let's get on with it. Our goal is to design a schematic standard for a Factorio circuit, such that, given the schematic, you can build the circuit in-game very easily. And conversely, if you have a circuit in game, you should be able to draw the schematic very quickly on paper so that you can begin to analyze what happens. And I want the schematic to show all the conditions of the combinators or the entities that are inside this circuit network. Because in game you have to click on each of the entity and check what happens inside, and that can be a really big problem that takes a lot of time. So I want to represent this concisely. And next, I want it to be something that we can use as a reference to analyze the behavior at each tick. Well, in the sense that if sometimes you can have a circuit that's time sensitive, maybe you have an input that changes rapidly, and you might need to analyze what happens over each tick. Now here's the standard I propose. For each entity, say each combinator or each machine, I would write a superscript and a subscript for the two channels it has, the red channel and the green channel. And if you have a combinator which has an input and output, it would have 4 channels. So I write the input on the left and the output on the right. So the input here I have a red and green, and I have an output red and an output green. Now if an entity outputs a signal S, we know that the outputs do not have a color. So if you connect a red wire to something or a green wire to something, the signal you get from its output is going to be exactly the same. So here we write something that does not have a color. We write for the entity E out to be the signal S. And we want to reserve some letters, so I want to use S for signal always, R for red channel, and green for green channel, A for arithmetic combinator, D for decider, and well, I want to use S for selector, but S is already used, so I'll write SE for selector, and E for a generic entity, such as a machine or an inserter or a belt. If there are multiple items with the same letter, I'll just write D1, D2, D3, say for 3 deciders. Okay, so if I follow the rules I just listed, I would be able to express a circuit network as a bunch of entities with some channels attached to them. But you might have the problem with, well, how do I construct this? It doesn't show where the entities should be or what the wires should be. And the idea is that it doesn't matter where they are, where you place them. As long as the wires are connected correctly, as long as you connect this R1 channel to this R1 channel to this one, everything's going to work. So this is a perfectly sufficient way of representing the circuit. Well, except we don't have a way to record what happens inside each combinator or each entity. So I would say a constant combinator outputs the signal S. So we want to write down C out is always S. A decider combinator takes a condition P and outputs S if P is true, and it outputs nothing if P is false. So here I would write D out is equal to S, and with a square bracket of P. Now, an arithmetic combinator computes a value x, and then you choose a symbol x to output, and the output is going to be written as a out, which is little x copies of this symbol x. And for selectors, I'm not going to cover that in this video, but for entities, I can just write down what they are. So I can write, say, chest read content, or if it doesn't output anything, I can write, say, inserter set filter. And if I have a channel, I would want to extract the number of some item from that channel. So I would write this round bracket. So for example, if I have a channel R1, the number of x's inside this channel would be recorded as R1 of x. So with the conditions recorded, our example here would become something like this. And yes, so with this, you can easily construct the circuit in game. You just place down the combinators and the machines, and then you connect the wires according to the labels here, and then you click into each machine and put in the conditions. So for this specific example, I have a circuit that has an arithmetic A outputting into G1, and G1 is used in D2 and D3, and D1. But D2 and D3 outputs into R2, and R2 is used again by A, so there's something circular happening here. So it's going to be somewhat complicated to analyze what happens in this circuit. So let's see how to do that. So I want to write at each tick T, I want to write a superscript of round bracket of T to represent what the channel is at this tick. So for example, I can write R1 of 5 to represent the 5th tick. And the output, I would also use a similar notation. I can write E out at the Tth tick. Now this is how you analyze what happens in the circuit. If the current tick is T, or if you're starting, you would set T equal to 0, then we write down all the signals stored inside these channels, the red ones and green ones. And if you are initializing the circuit, just set everything to 0. Next, you calculate the output of each entity for the next tick. So you compute all the values for tick T plus 1, and suppose you have a combinator that takes input from a red channel and a green channel, then you would use the information from the thing you just recorded in the last step as the input values. And after you computed all the output values, you combine them. So if you have a channel, say R1, and it has a few machines that all output into R1, you would sum them together. So I would say for each channel star, the information at tick T plus 1 is the sum of all the outputs such that the entity is connected to this channel. The entity output is connected to this channel. Now you have the information for T plus 1. You can either go back to step 2 and repeat and go further into the future ticks, or you can make a conclusion about what happens with this circuit. Next, we have an example of a memory cell. The memory cell outputs the sum of all the foreign input it receives for every tick since its birth. So what do I mean by that? The idea is that you have an arithmetic combinator A that has the input is connected to the output, but you also connect this green input, which comes from some kind of outside entity E. So I'd say E is a foreign signal that could be pushed into this memory cell, and the red channel represents the memory, and the green channel represents the input. And I say the output is equal to the red plus green times this symbol X. So what happens for this memory cell is, suppose at tick T, the memory inside the red channel is N times X. And I want to push in X times X from this green channel. Then what happens is you have these two channels. The output for tick t plus 1 is you replace this R1 by this value and and G1 by this value. So it's n plus x times x. And then you combine all the channels, you get indeed the t plus 1's tick for R1 is the combined signal now. So it remembers that last tick you have pushed the value x into this value that already has n. And then for the tick t plus 1 of the green channel, you could have the next input, or you could have nothing. And in the t plus 2 tick, the red channel would also remember the next input. So that's what a memory cell does. It remembers everything you push into it. If we consistently push one copy of x into the memory cell, then it's going to count up by 1 every tick. So in particular, a memory cell can become a timer. Okay, but what if we want to store what if we want to remember more than just one symbol x, but a wide range of various different symbols? What you do is that instead of just taking the value of x, you just do the value of each, and then it remembers everything. So I think this I have illustrated how to use my schematic to figure out what happens in a circuit network. And if you ever come across a circuit network that you can't figure out what's happening, or you're troubleshooting, maybe come back to this video and try to follow this approach. I think that would help a lot. And here is it's kind of a bonus example, because the examples we did before is kind of simple. It's just one combinator, so what's the big deal, right? Let's see something more complicated. So suppose I have a constant signal that's an input, S0, and I want to restrict to the symbols that have the highest value. So you could have multiple symbols that have the highest value, and I want to get all those symbols. So here's the implementation. You see there's a lot of things going on, and again you can build this really easily in game, but now we want to figure out what happens. So what do you do? Again, start with tick 0. You initialize. There's no values in any of the channels. Now you compute the output. The constant output just comes from the output. The constant combinators are always going to have the same output, so these are just the same. And the deciders, the deciders take these conditions, but for now we need to substitute the zeros tick into these conditions, but everything is 0 and the output is going to end up being 0, so we have zeros all everywhere. And now I combine all the output into the channels, into the green channels and red channels, using what I've recorded up here. So if I see the output of C0 is 3a plus 5b, I would look at C0 and see that it outputs into R1. So I would put a copy of 3a plus 5b into R1. If there are other entities that output into R1, I would also add their output into R1. So in the end, you get this. By the way, we're doing an example where the input is 3a plus 5b, so we expect the output to be 5b. Next, you go to tick 1. You just copy whatever you got from the last time. Now it's the information for tick 1. And then you substitute all the values up here into the conditions, and you compute the outputs to get these numbers. And again, you look at the output channels up here, and you sum them together to get the signals at tick 2. Then you repeat at tick 2 whatever, you get these numbers, and you substitute and get the outputs, and then you compute what happens at tick 3, and then you do tick 3 and output, and tick 4, and tick 4 then output tick 5, and after tick 5 you'll notice state 5 is the same as state 6 if you do this computation, which means the signal stabilizes, and our final output is into this power pole, which is the channel R3, which is 5B. So you indeed get the right answer. And when you perform this computation, you can just be an emotionless machine. Versus in the game, you have to check, oh, what happens to this combinator, what happens to that combinator every single tick. Here you just write them out, and it's really easy to see. Here's a quick explanation of what happened in that circuit. It's always going to be hard to explain something that's designed mathematically. But in application, when you do your own circuit, you're probably going to be troubleshooting what happens in your circuit, and in which case you would know what you should expect the circuit to output. And so using my method, I think you can do the computations and compare with your expectation and to see what has gone wrong, why your circuit is not outputting what you expected. And that's it. Thanks very much for watching. I hope this would be helpful, and if you ever find yourself troubleshooting, maybe try my method. Thank you.